All right, let's begin the proof to this corollary to the inverse function theorem. So let's assume that G is an open subset of E. So, well, let's assume all the hypotheses. Assume F from E to Rn is C1, with the E subset Rn open, and assume f prime x is invertible for all x in E. Then let G be open. Okay, and you don't have to worry about, open in the subspace E versus open in Rn. They're the same because E itself is open. So not worrying about that now. Okay, and our goal is to prove that the image of G under F is open. So let's focus on the points in G. For any x in G, do the following. I shouldn't say for any, for each. Do the following for each point in G. So our assumption is that f prime x is invertible for each x So for each x, we can apply the inverse function theorem. So for each x in G, the inverse function theorem provides a u. Let's call it u sub x, because we're doing this for each x in G. It provides a u sub x. Let me phrase this a little differently. Provides an open neighborhood, u sub x, of x, such that the image of u sub x under F is open. So for each x in G, we're going to use the inverse function theorem to get a neighborhood of x that F maps to an open set. Now, the problem is that u sub x is not necessarily a subset of G. And sure, I could intersect u sub x with G and I would get an open neighborhood of x, but then I wouldn't know that the image is open still. Well, I do know that, but I don't know it just from this part of the inverse function theorem. So I actually need more from the inverse function theorem. I kind of need all of it. So not only is f of ux open, but also f restricted to ux is an injection, and f restricted to ux inverse, the inverse of that injection, is a C1 function. So actually, I only need the continuity part of that. So let me just use what I need. I think I only need the continuity part. So C1 function means differentiable and the derivative is continuous. I just need that it's itself continuous. I don't even need differentiable. Okay, now u sub x intersected with G, I can show has open image under F. So let's define, I don't know, I don't want to call it V. How about W? define W sub x to be U sub x intersected with G. Then the image under F of W sub x is, well, it's the W sub x is a subset of U sub x, so there's no harm in restricting to U sub x first, right? And I want to look at this as the preimage of an open set under a known continuous function. So this is going to be the preimage of Wx under the following known to be continuous function. F restricted to U sub x inverse. So let me try to make this clear what's going on. I know that this is a continuous function, and here I'm taking that continuous function, and I'm taking the preimage of a open set under that continuous function. So that is open. Great, so what have I achieved here? I've done this for each x and g, right? So I kind of indented this portion of what I'm doing for each x and g. And now I'm going to stop indenting. And what have I achieved? So now we have a family Wx running over all x and g of open sets such that this, not just open sets, open subsets of G, well, yeah, let me put it this way, of open sets such that two things hold. Such that they're subsets of G, and each W sub x contains x, it's a neighborhood of x, and this is open. This is for each x, for all x. All right, then I claim, and these kinds of things you have to kind of think about carefully, that the image of that f of g is the union of these open sets. The union of this family of open sets. The union of these images running over all x and g. So definitely G is the union of the W sub x's, given this. But what I'm claiming here is that f of g is the union of f of the W sub x's. And I'm always a little bit scared with just concluding those kinds of things too quickly. Because, you know, we don't know that f is injective or anything like that. So let's just get both inclusions quickly. So this inclusion, if x is in G, then is x in this, is f of x in this union? So then f of x is in the image of W sub x, because x is in W sub x. So then f of x is in this union. And for this inclusion, if x is in any one of these, f of W sub, sorry, not x, let's call it y. If y is in any one of these, then y is f of something where the something, the x, is in w sub x, but that's a subset of g. So y is f of something in g. So that's it for that claim. Okay, and so we've written f of g as a union of open sets, and so f of g is open. So that's because it's a union of open sets, and the openness of these is what we proved here, up here, that they're open. So you see how we needed to use the inverse function theorem to do that. All right, and that's the corollary. So this is a way of proving that maps are open.